Hi, in this video I'm going to go through the Monocular Visual Odometry example from the MATLAB Computer Vision Toolbox. In this example, we are going to determine the orientation and position of an observer in a video coming from a computer animation, a synthetic video. And this is a strategy of using computer animations for is pretty common in automated driving for deep learning, but also for testing SLAM algorithms, as we can see in various computer vision examples from MATLAB. And the advantage is that it's cheap and we have the exact data, as we're going to show here. We're going to take a trajectory in this animation in which the observer goes to a desk and it gives a turn and goes behind the desk. And we have all the trajectory information coming from the animation, and we can use that to compare it. For example, here is the front, and near the end it's going to go to the back like this. It's going to take this trajectory, so we have all the information and we can compare them against the algorithm. Okay, how do we compute the position? Basically, we are going to use points in consecutive image. The example is called monocular because we are not using stereo. In stereo, we have two images for each frame, and with those and with the pairing of the points in stereo image, we can determine three-dimensional points. But we cannot do that in here because we have a single camera. So instead, we do the triangulation of points between consecutive images. The functions and concepts used in this example are the same that are used in SLAM algorithms. But here we only determine the orientation and position of the observer. In the SLAM algorithm, in addition to determine that, you also have to determine the map around you, the map of the environment through the three-dimensional points that you obtain through triangulation between these consecutive points of interest in frames in images. Okay, so these SLAM algorithms, and in this example, use a important structure that MATLAB Computer Vision Toolbox provide, which is called imageviewset. It contains a set of images, and for each image, it's going to have three important concepts. One of them is the identifier, which is a number from 1 to n. It's like an index in a database. It contains the orientation and position of the camera at that particular view, and it contains a set of features. In this example, we're going to use surf points, but you also can use orb, brisk, or fast points or other points of interest. And in addition to those features, you are going to pair them between consecutive frames, so you make connection between this view and that is captured in this object. So, for example, you're pairing the point number 1 to point number 2 in the second image, or point number 3 to point number 100 in the second image, and that pairing is used for the triangulation, so that information is also captured. And with that, you can derive poses and also track a sequence which we're going to see in this example. Okay, to start the example, I included the link to this example in the description of this video. You just hit open live script and you go, and that'll bring you to here. So I'm going to put a breakpoint here and hit F5 to run the example. But before doing that, I'm just going to run the video so that you can see the video. I'm going to clear all we're just going to run the video so you can see it. So this is how it looks. It's going to go to the desk and it's going to go behind it. Okay, at the beginning, the trajectory that we're going to compute is going to be very similar, but it's going to diverge from the actual as we go forward. So we need to make some adjustments, and we're going to use the bundle adjustment method that I'm going to go through that also. Okay, so now I'm going to put breakpoints. I'm going to just clear everything to start all over. Let me go from the beginning. I'm going to put a breakpoint here to start from the beginning, and also there's some helper methods. The example looks quite small, but it has a bunch of helpers, so I'm going to put a breakpoint in each one of them. So I'm going to give pause to do all of this. Okay, I'm done, so I'm going to run it. the first step is get the video, which is sequences of images, and I'm gonna capture it as a data store, as an image data store, which have a sequence of files. And this is the same structure that it is used for deep learning, for convolutional neural networks, to basically train them and to use the networks. And for the ground truth, it is stored in a math file, and we go to the workspace. We only have the image data store. After loading that math file, we get this structure. So we're gonna take a look at it, and the structure has nothing but the expected position and orientation for the camera at each frame. Frame number 1 goes from 150 frames in total. So let's take the orientation, the last one. The first one is going to be an identity. Let's just take it. It's an identity, and the last one is more real numbers. Okay. It's a 3x3 matrix rotation. Okay, so let's create the image view set, which is empty at the beginning, and let's read the first frame and just put it into a video player. Okay, so since the camera comes from the computer animation, we know the focal length, the principal point. So with that image size, we're going to create an intrinsic object, and this intrinsic object is going to be part of the parameters to triangulate and do the computations of the orientation of the camera. Okay, this comes from the camera properties. If you're in a real camera, if you're using a real camera rather than an animation. Okay, for cameras, usually the image can come distorted, so you use this undistort image function that takes an image and the camera intrinsics, and it's gonna undistort the image. But since this is coming from an animation, this is not really necessary in this example, but just to show it's being called. Okay, so as mentioned before, we are gonna determine the position of the camera as we go through the video by matching features of interest between successive frames. So we're gonna use serve features, and we pass the image and we take the serve features. We're gonna pick 200 with using this function that selects with a uniform distribution 200 points out of the 600 plus features that we have. Once we have the 200 points, we pass it along with the image to this MATLAB Computer Vision Toolbox function called extract feature, which is gonna get a vector of 64 real values for each of the 200 features. So this is gonna be 200 by 64. So for example, for the first point, we have 64 values, real values, and this is important because if you have 2 points in 2 consecutive images, you're gonna use those 64 values for each one of those points to compare them to see, okay, they are close enough, so they really belong to the same point. And once you have 2 points in 2 different images, then you can start the process of triangulation. Okay, so now we're gonna create the first view. And since we start at the origin, the rotation is going to be identity matrix, and the position is going to be 0, 0, 0, and the previous points are the one that we just got from serve. Okay, the 200 points. And the view ID is going to be first one, so it's going to be 1, and we added to using this addView method from the image view set. Okay, so let's plot the camera. So we're gonna do some commands to change the orientation of the plot. This is just a plot, and the labels for it. And the size of the camera in the display is gonna be 7. And there's a method in the image view set called poses, which is gonna get you the poses of each of the views. Right now we only have one view, and this rigid 3D is gonna give us the orientation of the camera. Okay, so we pass this camera pose, and this gives us the position and orientation, and we display it with a green color. And with a blue color, we're going to display the actual one, which comes from the orientation and the location that the ground truth object from the map file that we loaded. This is the reference. So as expected, both of them are on top of each other because they start being in the same place. There's nothing special there. Okay, so now we're gonna get the second frame. We're gonna go to view number 2, read the second image from the image data store and put it into the video. It's not much different from the first because the camera is moving slowly. So again, we understood the image, and we are going to use this helper detect and match features method, and that what it's going to do is the same that we did before. Get the served features, select some of them with uniform distribution, and extract the features. But in addition to that, it's not only to detect features but also to match them. So we're going to pass the previous features. These are the 200 by 64 features, and as mentioned before, for each of these 200 points from the previous image, we're going to match them against the points that we find in this image. So we pass the current image and the previous features. Okay, let's go there. Okay, so we're going to pick up the served features from the current image, and how many points we have? 600 plus again. We're going to select only 150 with a uniform distribution, and again we use the extract features to get the vector of 150 by 64. Okay, now we provide the 200 from the previous one with the 150 feature from this one, and using the feature vectors, we're going to match them with the match features function from MATLAB Computer Vision Toolbox. And what this is going to return us is an index pair. And this index pair, I think I mentioned it before, that when you add a view, you add the orientation and rotation of the camera, but also the features for that particular image. And then you connect two views, and when you connect two views, you have to put a map between the feature points in one image and the feature points in another one. And that map comes from this method, and we're going to see what this returns. Is two columns that gives you the index of the feature point in the previous image to the index of the features in the current image, previous versus current. Okay, and as you can see, we provide 150 points and 200, but the index pair are less than that, 102. So not all of the points match. So we lost some points, which is expected. Okay, so now from this method, we get the current points, the features for those points, and the pairing with the previous features. Now we're gonna estimate the relative pose based on those points between the two images. Okay, so we have the pairs. Column number 1 is the pairs for the previous points, so we're gonna use that to filter. We have here 200, but out of this, we're gonna get 102, and the same goes for this one as well. It's gonna give us 202. So the second column is for the current points, and the first column is for the previous points. Okay, and also we pass the camera intrinsics, because with that we're gonna estimate the pose of the second view, which is the second image that we're processing right now. Okay, so we're getting the locations, the two-dimensional locations from the first points, and two-dimensional location from the current image. And this time we're going to use the essential matrix that is determined through the camera parameters and through the points between the two, because we know that these 2 points belong to the same places in the world. And given the camera parameters, we can do some type of triangulation. We're going to actually use a triangulate method later, but right now we are using this essential matrix, which is something similar. And with this essential matrix, we get the points that actually contributed to it. And so there's 102 points, but out of those points, only 96 were used. So we sum and the number of elements. If the ratio is too low, is because not many of them were used. In this case, many of them were used, so we filter them out. So we have 96 now, rather than 102. And then we use relative camera pose function from the MATLAB Computer Vision Toolbox that takes the input, the camera parameters, the intrinsics, takes the essential matrix, which is basically like a rotation matrix, 3 by 3, and the previous points, 2-dimensional points, and the current points. And notice that we're taking from 1 to n, but with a step of 2, so we're taking half of them. Okay? So once we compute the orientation and location, now we have the 3 by 3 orientation and the vector, the 3-dimensional x, y, and z position. But the valid fraction is 0.18, and we want a valid fraction of 80%. Okay, so we're gonna try this 100 times, and let me see, I run it, and eventually in iteration number 2, I was able to find a valid fraction of 95%, which is good enough. So now we have the orientation and the location of the second view. Okay, and with that orientation location, again, not all apply, so we're going to filter some of the pairs of the index. And with the current points that we obtain from help and detect match feature, we can create the second view. We have the orientation and location, so we can create the second view, but now we can also connect the first view to the second view. And the connection is done with this method. Both of them are methods from the imageviewset object that contains all the views. So add connection is going to connect the second view with the previous one. View 2 minus 1 is 1, the previous one. And then this is the pair of features that we obtain from match features, matching the features in both images. Okay, and this is important to create the track object, which we're going to see later. And the track object is used for the bundle adjustment function. This function that is used in SLAM is basically to adjust the trajectory based on 3-dimensional points and the positions of the camera so far, the poses. We're going to see that in a moment, but that's one important thing of keeping track of the features between images as well. Okay, so we add the connection, and now we're going to normalize it, which is a little, this is some type of hack. Basically, it's going to take the poses from this poses method from the imageviewset. It's going to give us the poses. So far, we only have 2 of them. The first one is the origin, and the second one is the one that we just computed. From the locations, we're going to subtract the base location, which is basically the 0, 0, 0, so this is useless in this case. So we're going to take the locations from the ground truth and the locations that we have calculated, and have a ratio of median and magnitudes between the ground truth and with that we have a scale factor, and that scale factor we apply it just to make the translation more similar, and then we apply that to the camera poses. And with this update view method of the imageviewset, we set the new poses. So the next time that we call poses, we're gonna get the one that we set in here. Okay, so that's it for normalization. It's kind of a calibration with the ground truth. Looks to me a little hacky. Okay, now we're going to call this couple of methods to basically update the plot of the cameras for visualization. And the first method is just going to pass the pose and orientation from the estimated and the actual to the cam estimated and cam actual. I'm just going to copy to this structure. And then we pass the actual, and those 2 objects are going to be used to update the lines. And we also pass the poses from that we have computed, and also the ground truth poses. And with that, we go to here, that we got all the location, the 2-dimensional locations of the poses, and we just plot. It's basically setting another point in this line It's a color line of color. I think it should be green. Yeah, this is the green color, and the other one is the blue color. So with this is the ground truth. So we're gonna plot the line, get the three-dimensional point, and just put it into a three-dimensional plot. Okay. Okay, and now we just run, and now the current points and current image and current points become the previous one. So we're gonna keep iterating through that. So it's no surprise the estimated and actual are the same. The cameras go from the same place, original place, don't deviate much at the beginning. So now we're gonna enter the for loop, and we're gonna do the same multiple times. We're gonna execute it 15 times, and in this case, we're gonna do some additional computations. We're gonna do some filtering through Bipolar Inliners, and we are gonna use bundleAdjustment, which is a function to recalibrate the camera poses for the imageviewset. But we're gonna do it each frame. This is an expensive computation that depends on triangulation of the tracks, and in the other iteration, it's gonna pick up the rest of the file, which is about 130 iterations in here. And in this one, we don't do the filtering, and we do the bundleAdjustment only once every 7 iterations. So it's less expensive, but we're gonna notice that in the first 16, 15 iterations, there's no much deviation because we pay the price of computations of the adjustment. And in here, it's gonna give some deviation, but eventually with this, it gets adjusted into the trajectory. Okay, so let's run it. And also another thing to notice is that to compute the pose, we used previously this help estimate relative pose that used the essential matrix to compute the relative pose, but we're going to use a different function in here to estimate the pose. We're going to see how that works. Okay, so first we're going to read the third image. We're going to put it on the video. We're going to undistort it, and then again we compute the current points and match them. So we get the matching between the second and third image. This is the matching of the points, 98 point matches. We get new features from surf features, and also the vectors. Okay, now we're going to filter using Bipolar Inliners. Okay, it's just basically filtering some invalid points. So we're gonna use again the helper estimate relative pose, which is gonna use the essential matrix. This is the same method that uses the essential matrix, and with that we're just gonna get some index, 98 matching index, and with that we basically filter some of the pairs that we obtain from the feature matching, the match feature function. Okay, so now we filter 10 points out of the 98. Now we have 88. That's it. Okay, so now using the index pairs that we obtain here, the camera intrinsics, the imageviewset, we're gonna basically determine some three-dimensional points associated to those index pairs and the corresponding three-dimensional points, and those are going to be used to estimate the pose and orientation of the camera in the current view using this function from the MATLAB Computer Vision Toolbox. Okay, so let's get inside of here. This one of the most important functions. Okay, so again, from the imageviewset we get the poses, and from the poses we get the previous one. We get the translation and rotation. So here's the location, which is the base one, orientation is I, and then we just basically this is the same. And then we use this function, a MATLAB Computer Vision Toolbox function, camera matrix, that takes the intrinsics of the camera, the rotation, and the translation, and it's going to create a camera matrix, a 4x3 matrix representing the rotation and the position of the camera. Okay, we're gonna do the same for the current view, which is the n, the last one. This was n-1, previous one, and this is the current one. Okay, again, we get the location, orientation, and it's a little different Now, yeah, previously it was the same, but camera pose to extrinsics. Okay. So now using the camera intrinsics, we get the camera 4x3 matrix representing the position orientation. So we have the two matrices representing the rotation and position of the cameras, the previous one and the current one. And now all we need are the points. So how we do this? Again, as mentioned before, when we connect two views in the image view sets, we have these connections. So we get the last match. And with that, we get a pair of features. And this is the previous one, the last one, because we have not made a connection for the current view. So the match that we get is the one that we just obtained from the serve and match features methods. So in here, it's a little bit hard to see, but the first column belongs to the previous image, and the second column belongs to the current image. Okay, so let's say that this is in the view number 3, and this is view number 2. Okay, the previous match, you have the view number 1 and view number 2. So we're picking up column number 2 that belongs to view number 2, and here we could pick column number 1 which belong also to view number 2. So we're picking the indexes that belong to the same view, which is the number 2, and get the intersection. So the index for this one, for the previous one, and the index for the second one. So we're using the index for the previous one and take the points of the view number 1 in here. This is for the view number 2. And then we use this index for the view number 2. Actually, no, basically with this index we take the column number 2. So we get the points in the current image. So this is the index in view number 1, view number 2, and view number 3. And then we get the points from the previous view and the current view. And with this one, this is view number 1, so we take the view number 1 index, and this is view number 2, so we take view number 2 indexes, and the camera for the previous one and the next one. So we basically are triangulating, doing a triangulation between the features of the first and second view, but we're processing view number 3 right now. So we're taking advantage that we already have a view number 1, view number 2, and we can triangulate to find the three-dimensional points belonging to those points that we already match. So the index here are 69. And notice that the matches are 98 for the previous one and 88, but with intersection we have much less. We have only 69. So we're only going to pick up 69 points out of the points. So for each of those points matching, we're going to find a corresponding three-dimensional point, and this is what we're going to return. And also we're going to get the corresponding two-dimensional points in the third view, which is the current view, the current points, and get the location. So we have the three-dimensional points that is and the mapping to the two-dimensional points in the current image. So we have the real world points mapped to the current image. And let's return just to take a look at how this looks. So you can see we have 69 three-dimensional points and their corresponding 69 two-dimensional points in the current image. So with that, we just pass the two-dimensional points, the 3 points in the current image, and the intrinsics of the camera, and using this estimate world camera pose, we can estimate the orientation and location of the current view. This is a three-dimensional rotation and the XYZ of the position of the camera. So with that, we create the current view, and we pass the current points, and we already have the pairing obtained from the match features function. And that's going to be used to connect the view number 3 with the view number 2. And we just created a view number 3. Okay, so we keep this process to keep getting the orientational location, to keep doing this triangulation between the previous views, the previous two views, to get the current view. Okay, so now we use this find tracks method, which returns this interesting object. And basically what this is gonna do is find points, find different points. In this case, we find 117 points that can be in multiple views. I mean, it's not just two consecutive views. A point can span 1, 2, 3 views. In this case, we have so far 3 poses. We're gonna see it in here. So how far we have collected 3 views. So let's take a look at the tracks again. Let's take, for example, the first track. And notice that this first track has 3 points that appears in all the 3 views. So this is a real 3-dimensional. This belongs, the first one, all of them, each of the tracks belong to a real 3-dimensional points that is visible through the views, through all the views available. In this case, all the views. Sometimes if you have, let's say, 100 views, it might be in view number 55, 56, 57, and that's it. It could be more. So basically, it's going to tell you in which views you can find it. And this corresponds to dimensional views, to dimensional points in each of the views. And you can see that they differ a little bit, but not that much. And this is expected because the camera is moving in the video, so the points are moving as well. So that you expect a slight movement of these 2-dimensional points as the camera moves. Okay, so in this case, the feature corresponds to feature number 1 and 1 in each of the 3 views, but that's not always like that. Let's take the track number 70. So you can see here that this particular point had different feature indices in different views. So that's pretty normal. And again, the points for these are different but very similar because there's like a continuum in these points. That's why it's easy to detect the matches between them. Okay, so now with this triangulateMultiview, we pass the tracks, we pass the poses. Both of them are coming from the imageviewset, and we pass the camera intrinsics, and we can determine the corresponding 3-dimensional points that belongs to each of those tracks. Remember, we have 117 tracks, so we're gonna have 117 3-dimensional points belonging to each of those tracks, because one track belongs to a real 3-dimensional point in reality. Okay, with the tracks, the 3-dimensional points, the corresponding 3-dimensional points, and the camera poses, we can use the bundleAdjustment method along with the camera intrinsics, and now we're gonna get a camera poses. So we went through all this work of triangulation of the points, getting the tracks and the poses just to adjust the camera. So as we go on and collect orientations and rotations of the camera and collect matches of points, we can use that information to adjust the positions of the camera to make it more consistent with reality, and that's what we're doing with bundleAdjustment. Again, as I mentioned before, this is an expensive computation that you don't have to execute always, but it's good to execute to recalibrate the camera's trajectory as it diverges from reality. Okay, so now we have new camera poses, so we use the update view, pass the new camera poses, the 3 of them, to the imageviewset, and normalize again using the scaling relative to the ground truth poses. And then again, now that we have a new orientation and position, we're gonna put that into the line trajectory for visualization, and the current image becomes the previous and current feature becomes the previous features. So we're gonna execute this 16 times. So I'm just gonna run it and gonna wait to here, and as expected at the beginning, it doesn't diverge that much. We're going through the extra computations, and so it's not far from reality. Okay, So now, as mentioned before, we're gonna execute this for the remainder 130 something images. Okay, so again, for the rest of the computation, we're gonna be less expensive. We get the image, put it in the video on the store, get the matches, the features and their matches. Again, use the same method that computes the camera. It's like we're in position number n, so it's gonna take a n-2 and n-1 views, get the corresponding camera positions, get the corresponding features, do the triangulation, and get the matching of the three-dimensional points to the two-dimensional points, and use the estimate world camera pose along with the camera intrinsic to determine the orientation and location of the current camera, add it to the view and the pairing of the features, and to update the image view set. And for each 7 iterations, we're gonna get the poses, get the tracks, do some triangulation, and use the bundle adjustments to calibrate all the poses that we have accumulated so far, and then again plot it in the 3D plot. Okay, so I'm just gonna let it run, and we can see here that at the beginning it doesn't diverge that much, but it starts to diverge and then it calibrates. This should be the bundle adjustments in here, and then it diverges, and the bundle adjustment should get it closer again for each 7 iterations. Okay, so there's kind of a trade-off in there. So yeah, I'm gonna run it again in here. So if you want to be very close always, you can execute the bundle adjustment for each iteration, but that comes as an extra cost. If you don't bother being a little bit separated like this from time to time, then you can omit that, as in this example, do not compute bundle adjustment every time, so that you can execute faster. So it's a trade-off between accuracy and speed of computation. So that's all for the video. Thank you very much for watching.